All right, good morning, everybody. Happy Tuesday. You have your exams. If anyone slips in or just got here in the last second, you want to grab your exam, feel free to just wander up and grab your exam whenever. I will just ignore you. I promise. Maybe. All right? So let's see a few things. If there are questions about grading, if anything looks like it's incorrect or you're just not sure why points were taken off, or I don't know, just numbers could be added up wrong, like any sorts of things that just appear to be off. Mistakes are common on grading, so just let me know. I'll take another look at it, and if things seem to be wrong, we'll make the correction, okay? You can talk to me after class, or if you want to just take a picture of what the issue is, you can send that to me, and I can review it that way as well, okay? So I'll try to be as fair as possible and catch any mistakes that are out there, but I do rely on you a little bit for that because stuff happens, all right? With regards to homework, homework was due over the weekend, but I did send out an announcement that I've decided to reopen that and extend it because there were quite a few emails that I just didn't get to, and it doesn't seem fair that I haven't replied to all of your emails that had questions about various problems and stuff. So to give me a chance to kind of get caught up with that and also to give you more of a chance to get more points, the homework is back open. So all first 5 assignments are due on the 25th now. They're all going to be due on the 25th. So the later assignments have been pushed back a little bit as well to give us some time to cover this new material. But keep in mind, more assignments are coming. So don't put them off thinking like, oh, well, if those are due on the 25th, it's going to be like weeks until there's more due. I wouldn't count on that. Maybe there'll be some due on the 26th. Dun, dun, dun. Probably wouldn't do that. But it could come quickly just to make sure that we are learning the things that we need to. Okay? Let's see. Anything else? I can't think of anything. You got any questions for me? Yeah.
You said the average was 63 or something like that?
That sounds like something I might have said, yeah.
Does that mean you're...
I don't know yet about a curve. I'm pondering the whole situation. I would prefer to wait till the end of the semester, but I might not. I don't know. I'll let you know as soon as I decide.
So if you didn't do so well on this exam, and those types of questions are going to be on the final. And
They will be on the final.
4 points for those will be replacing the first exam?
Mm-hmm. So yeah, you do have another chance on the final exam. Part 1 of the final exam, if you do better, will replace this exam. It'll be like it never happened. But if you do worse on that section on the final, I won't go back and replace it that direction. That'd just be mean and weird and pointless. Okay? That's part of why I hesitate to give a curve now, because there's kind of a curve built into the structure of the course by giving you a chance to redo, but I may anyway, because I don't know. Just need a little more time to think about it. Okay? Do you have a question too?
Yeah. In general.
In general.
Which questions did people get?
In general, which questions did people get wrong?
Which ones were like the baddest?
I haven't looked to give you an exact answer. My guess is 2 and 3 of the overall problems, and probably a lot of multiple choice were missed, because that's pretty standard, but I don't have the numbers to tell you quantitatively. Is there a hand back there somewhere too, a minute ago? I thought there was. Maybe your question got answered. I don't know. All right, so today we are continuing more of the same, which may be good or bad depending on your perspective. We're not covering brand new things in the sense that we're going to do more with forces. And kind of step up the level just a little bit. So if you were struggling with it before, we're going to talk about it some more. So you've got more chance to kind of absorb the information, especially as we talk about it from some new perspective and stuff. If you already understood the forces stuff so far, you are primed and ready to go to kind of add on to that knowledge just a little bit. So both today and Thursday, we're going to continue talking about forces. So I called this whole file like 5B and Chapter 6. It's kind of a merger of the two, some things we left out of Chapter 5, together with everything in Chapter 6, okay? Once we finish chapter 6 and this set of slides, we're going to change gears kind of dramatically into a new way of looking at some of the same things, okay? So before we can proceed into this chapter, we have a fifth common special force that we have to know about. What are the first four that we have? Gravity, normal, tension, friction. We're going to add to that spring, okay? The spring force, which we will represent with F sub SP. I'm going to go ahead and write the equation up here, and then we're going to come back and talk about it in just a little bit. Our equation for this is negative K times X. Negative K times X. So I'm sure we've all dealt with a spring at some point in our life, be it a little spring that's maybe, part of your pen, or maybe it's a fun spring like a slinky. Does everybody know what a slinky is? The toy. It's just a big spring that's really, really loose. Or maybe, I don't know, you're dealing with like a spring as part of the suspension on your car, and then it's a really, really tight, strong spring. A variety of springs. But the thing that they all have in common is that they sort of have a natural length, and they really kind of want to be that natural length. If you stretch them, they oppose you, and as soon as you let go, they just go back to whatever length they were. If you compress the spring, again, they oppose you, and if you let it go, it, well, for lack of a better term, springs back to whatever length was before. So it has a natural, normal, or what we might call an equilibrium length. Equilibrium in that when it is that length, it's just sitting there. It's kind of inactive. It's not exerting a force at all. So if we were to draw a diagram, a few different things here. Let's start with just a normal length of the spring. Isn't that the best drawn spring you've ever seen? Lie. Please lie. Lie. It's the best drawn spring you've ever seen. I understand. Let's say that maybe right here is x equals 0. This is when the spring is in its normal equilibrium length. It's just basically we took the spring out of our big bucket of springs, attached it to the wall, attached it to the mast, didn't stretch or compress it, and just set it there. And it's just going to stay there forever. Okay? There's no reason for it to change its position. Now, if I, on the other hand, take this exact same thing and then stretch out the same spring, well, now I'm no longer at x equals 0. Maybe now the end of this spring is at some positive x position. The spring is stretched. It's going to exert a force. Which direction to get back to where it was? Everybody point. That way, right? It doesn't want to be stretched. It wants to be back at x equals 0. So it's going to exert a force on the mass that's that direction. And you might guess we could redraw this one more time. Except this time we're going to go... Nope, I didn't like that. Let's try it again. Like this. Now the spring is compressed. So now the end of the spring is at perhaps some position negative x. And to get back to x equals 0, which way is the force going to be? See, I don't even need to really teach you anything new. You know what's going to happen here. So the spring force this time is this direction. It just wants to get back to equilibrium. That's all it cares about. That's all it wants in this life. Just leave me alone and let me be at equilibrium. Okay? So let's take a look at the values or the quantities that are in our equation. First of all, x. This is the position of the end of the spring. Could be positive, could be negative, just where it's located. If it's 0, clearly there's no force, right? Plug in a 0 there, you get 0 for the spring force. When it's in equilibrium, it's not doing anything. It's just sitting there, okay? If we have a value for k, which we must, this is known as the spring constant. It's a measure of the strength of the spring. So bigger values mean a stronger or stiffer spring. It's harder to stretch or compress. And smaller values indicate a weaker spring. If you take and rearrange that equation and solve for K, you get force divided by X, which gives me the units of the spring constant. It's newtons per meter. And those units literally say how many newtons of force the spring will exert for every meter that you stretch or compress it. Stretch it 1 meter, this many newtons of force. 2 meters, twice that much. 3 meters, twice that much, whatever the number happens to be. So bigger is more newtons of force being applied by the spring for every bit that you stretch it. And then finally, there's this pesky negative sign. And you might be thinking, what could be the big deal with a negative sign? Who cares about a negative sign? It's just a negative sign. How many times can I say negative sign? Right? It just, like, well, you know how to use a negative. It's not a big deal. Well, it turns out there's a ridiculous number of questions about this one particular negative sign for some reason. If you'd like your exam, we will all watch you while you find it. I told them I would ignore anybody who did this, but I'm not going to ignore you. You're going to look at that right on the top.
Oh, thank you.
Yeah, there it is. Enjoy it. Yeah. Burn it if you want to, or throw it out the window. It's fine. Whatever you need to do. All right. This negative sign means one thing. It means that the force is opposite to the displacement. The force is opposite. It opposes your stretch or compression of the spring. We have already used this negative sign, but you didn't think that's what you were doing at the moment. When we decided that, oh, if I stretch it this way, the force is going to go the opposite way, you dealt with that negative sign. You said it was the opposite direction. When I compress it this way, you told me the force was the opposite way. You applied that negative sign without even thinking about it, okay? So the negative sign comes into play when thinking about which direction the force is going to be. It's going to be opposite from whether you stretch it or compress it. It even works mathematically. Notice, if I move this and stretch it to a positive x, plug in a positive value for x times k, leaves me a negative sign there, I'm going to get a negative for the force. Positive x results in a force that points in the negative direction, okay? If I move this and compress it to a negative position, plug in a negative x, 2 negatives make a positive, yay, you can do that, right? Yeah. Well, now I have a positive force. Look which direction the force is pointing, in the positive direction. Negative position, positive force. Positive position, negative force. They're always opposite from each other, okay? So when we draw a free body diagram, we're going to consider that negative sign, and from that say, my force is this way. And once I've done that, that's all I need to do, okay? Much like when we have like a gravitational force and we draw it down, we've considered the direction, we've pointed it perhaps in the negative direction, but then when I plug in for mg, I just put a positive 9.8. I did the direction once. I don't need to like say it's down in the negative direction and then plug in another negative. That's double negatives. Double negatives make single positives. Single positives mean wrong in this particular case, okay? Point it down, you've considered the direction already. For the spring, point it in the direction it needs to go, you've already considered that negative sign. So we are often going to just consider, after we've done that, the magnitude, which is just k times x. I have an untied shoestring. Look at that. I'm probably going to fall at some point in this class. Has anybody ever actually tripped over their shoestrings? It seems like an overstated danger. You have? Yeah, no, never. Some have, some haven't. Probably on steps it's worse, I'm guessing. I don't know. Question?
So if you don't stretch it and if you don't compress it, the equation of the force would be, there would be a negative sign in there? Or?
If you don't stretch it or compress it, x is going to be 0, and we just won't use it at all. Okay? It only exerts a force if you've displaced it from equilibrium. Okay? Yeah?
Are we gonna end up considering like when you stretch a spring too far?
No, we're not going to consider that. Yeah, don't stretch a spring too far. Loses its springiness, and life is sad. No, we're not going to deal with that. Shall we do a problem with this? Yeah, seems like a good idea. So we're going to use this person. I don't know. Yeah. Seems to me that this person has a spring for hands. That's the only way that I can really interpret that, right? Because I don't see any hands. Either that or they're inside the spring. I'm not really sure what's happening. I think they have spring hands. So they just have to walk around like this all the time and try to do things with their spring. I don't know. It seems like a bad way to live, but you get the idea. So this person is attempting to drag a box to the right using a spring. Doesn't seem like the best way to move a box, right? I would prefer just a rope, but for whatever reason, this has a spring in it. Maybe this is one of your friends from in your younger days where they tried to push something with a rope, you know? Push with a rope, pull things with a spring. Neither one really makes any sense, but we're going to go with this anyway, all right? Now, if you can imagine what might happen here, when you start to try to drag the object, right? So I take my spring hands and I'm like, ugh. So I attach it to the table, and then I back up. You think the table is going to move right when I start backing up? Probably not, right? The spring is going to stretch. What if I keep doing that? Depending on the weight of the table and everything, I might just like keep stretching it and the box might never move, right? We're going to assume that everything else is such that after I back up a little bit, the table actually starts to follow me. The box actually starts to follow me, right? So you might imagine I step back a little bit, start to stretch the spring, and if I keep doing that, eventually like the table kind of lags behind, but starts to follow. And then if I stop, then the table would move just a little bit to recompress the spring. Everybody can see that? Okay? As long as I keep backing up and applying the force, whatever stretch there is in the spring when the table starts moving, it's going to sort of just maintain that amount of stretch until I stop applying the force. So the amount of stretch is going to be constant, first of all, while we're moving the box. Also, if I'm the box, which direction do I feel a spring force? Like on me right now, like where should I, like my arm is a vector. Where does the spring force go?
Toward the person.
Straight toward the person? Opposite toward the person? Now I'm just being strange, right? How about here? Anybody want this one? Yeah, let's talk about it just a little bit more, right? Imagine I'm the box. Don't be the spring. Be the box, right? You're sitting here, you're just like, okay, nothing's happening. Nothing's happening. You know, like something's dragging you that way. Sure seems like if I'm the box, like something is pulling on me up that direction, in addition to the ground supporting me and gravity pulling me down, and it looks like some friction dragging me that way, okay? So why do I feel a spring force up in this direction? Remember, the spring is being stretched, but really wants to just get back to the length that it was. Well, the person's not cooperating, right? They just keep backing up. So it's like the spring would maybe pull from this way and say, I'd like to go back to my original length, but like I just keep pulling the end of the spring this way and not allowing that to happen. Which means that it has no choice but to pull on the other end to try to recompress itself to its normal length. So if it's pulling this way, that explains a force up in that direction. Okay? A little bit convoluted in this first problem. Questions before we draw a free body diagram? Yes?
Are we going to like chop off the beginning where like the box would have to overcome static friction and then
We're going to let it go ahead and be
kinetic?
moving.
Okay.
Yeah. We'll assume that it's already accelerating this way. How's that? Okay. Free body diagram. Next step, and really the first step on these problems is free body diagram. So let's draw a mass. And if it's moving to the right, that will be the positive x direction, which means that upwards will be the positive y direction. And then I think you should tell me some forces that are acting on the box. We just talked about one, right? Which way? Right up this way, like that, right? Force, spring. Name another one. What was it? Normal force, which is perpendicular. I saw some mistakes on the exams. Some poorly drawn normal forces. Normal force perpendicular to the surface. So you can't just randomly draw normal forces off weird directions. Don't do that. If the surface is perfectly horizontal, then the normal force is perfectly straight up. Has to be perpendicular. Has to be, has to be, has to be, has to be, has to be. Okay? Name another force. Gravity always points where? Down. So on your paper, that's toward the bottom of the piece of paper, right? So on the exam, I saw some gravities going weird directions. I don't know what earth you live on, but it's not this one. Gravity points straight down, no matter what's happening, no matter where your x and y axes are, doesn't matter, gravity points down. And then there's one more. Friction. What type of friction is this? Kinetic. And which way does it point? Straight that way. Kinetic friction, because we're assuming we've already got over the hurdle of getting it started and it's accelerating to the right. This is my free body diagram for this problem. Does anybody see anything in there that you want to ask a question about? I'm going to take that maybe as a no, perhaps. So what's the next step after I've drawn a free body diagram?
What we know and what we don't know.
We don't even know what we're looking for. Might be, yeah. I don't know that we can write a list. We could write a list of variables that we have, but I wouldn't know what else to put in the list as far as unknowns. We'll have to see where something else takes us, yeah?
Shouldn't your friction be negative? It's pointing the other way.
Shouldn't it be negative? It is pointing in the negative direction. So it's pointing to the left.
Should it be negative now?
It will be negative in the equation. We'll use a negative there, yeah.
Add up the forces.
Add up the forces, but what do we call that? What was the name of that equation? Newton's second law, yes. So we're hitting all around it. So write down Newton's second law, which will allow us to add up all of the forces in the x and in the y direction. Always, always, always with force problems, free body diagram, and then those two things. If you go back and look at your exam, the force problem we had, part A, was draw a free body diagram. Then you had parts B and C. For one of them, you needed to start with one of these equations, and for the other one, you needed to start with the other. So it laid out exactly like the sequence of events you should follow to solve a problem like this, okay? Once we have these equations, we can look at the accelerations and say, okay, what's happening with the object? Is it moving? Is it moving which direction? Is it accelerating in that direction? Well, I've already been told that it's accelerating in the positive x direction. So that part of the equation, we're just going to keep just like it is. So I'm going to rewrite that. What about in the y direction? What's it doing vertically? Nothing, right? It's moving horizontally but not vertically, which means that this acceleration is 0. So I completed the right-hand side of both of those equations, which leaves us with the left side. The left side tells us add up all the forces. First one is add up all the forces in the x direction, and then the second one, add up all the forces in the y direction. So you will notice that we have this, which is in the negative x direction, and then looking over to the positive side, well, I've got a component of this one that will be positive. So let's go ahead and break that into components really fast. Got a positive x component and a positive y component. We'll say that that is theta. So the bottom side, the adjacent side, what is that going to be? Cosine theta times what? Times the hypotenuse, which is FSP. which means this side is going to be FSV sine theta. Okay. Now, if I were to just cover up everything that's not horizontal, maybe we cover this up, and cover that up, we can see that there's one force to the right, one force to the left. That's all that's horizontal. So let's write those down. My force to the left is negative, so that's minus F friction kinetic. And my force to the right is positive, so that's FSP cosine theta. Yay. Yeah, good. You're okay? Maybe? All right. What's happening vertically? Vertically, well, like this is not vertical, and I need like a narrower iPad maybe. Nope, it fits just in there. Look at that. Okay, you can see there's three forces. Two are pointing up, one is pointing down, right? So these two are positive, and this one is negative. So let's write those in. So I've got positive normal force, positive spring force sine theta, negative Fg. So we looked at the motion by looking at the acceleration, and then we added up all of the forces horizontally and vertically. You can do that, right? You can do that? I see some doubtful faces. Are you doubting me or are you doubting yourself? You can do that. You can do that. Now I'm using the force on you to assume, to make sure that you can do that. I'm also waiting on questions, but none have come, so I'll continue. We have an equation for the friction force. Do you remember what it was? Mu times what? Got half of it. Let's write that down. First of all, mu k times what? Not acceleration. Who remembers? It's in there somewhere. It's deep within your brains. You flushed your brains after the exam, didn't you? Yeah, like immediately. You went straight across the hall of the restroom and just like, and just emptied everything that was in there. Mu times what? Yes, mu times the normal force is our equation for the friction force. So I'm going to substitute that in. We just learned our equation for the spring force, which is, oh, come on. Negative kx, if we're dealing with the negative sign. I've already considered the negative sign, which makes it point up this way, which means all I have to deal with here is the magnitude, which is kx. So I've plugged in sort of everything that I can there, all the little mini equations that go into the bigger equation. Now, if I look through this, I know everything except the normal force and the acceleration. I wasn't given values for either of those, but I was for everything else. So I'm kind of stuck. I can't solve that equation. Done, okay? So let's go down here. Well, I, again, don't have a value or an equation for the normal force. I know this is kx, and I know the gravitational force is always what? mg, right? So let's plug those equations in. So normal force plus kx sine theta minus mg equals 0. And if you look through there, the only unknown is normal force, which means I can solve this one. So let's do that. Prepare your calculators. I need help. Help me find this answer. So let's see, that's going to be positive mg minus kx sine theta. And let's plug those numbers in. Let's see, the mass is 34, g is 9.8, k is 1350, x is this stretch that they're giving here, which they defined as an S, I guess, for stretch. I don't know. But it's in centimeters, so make sure you convert that to meters. And then the sine of the angle, which was 17. Somebody tell me what you get. Don't all tell me at once, though. I know you're dying to, but. 488. The air. All the air. That one stay open. No. Are you leaving? No. You can leave if you want to. It's fine. Let's use this. Now we just need someone to like stand at the end of the hall and hold those doors open, and then we'll have something. 285. I think that's about what I have. So 286 if I round it. 286 newtons. Thank you. And now that I have that, I'm able to go back up here and solve for the acceleration because now that takes care of the problem of two unknowns. So up at the top here, we can solve this for AX, which is minus mu k Fn plus kx cosine theta all over m. And you can plug those numbers in and tell me what you get. Once you get the answer, just shout it out with confidence, and then I'll either be like, yes, or wrong. But I'm not being mean when I say wrong, I'm just telling you it's wrong. You probably just hit a number. That's just a missed button. It's no big deal if you have a wrong calculation. Anybody? There's always like 10% who are like, I should calculate. I can do this. I will be helpful. And then there's also 10% that are just kind of like, I'm not going to do it. Nope, not going to do it. And then there's some in the middle that are like, oh, maybe I will. Maybe not. Somebody's got it. I should help, but no. Who's got the answer? Somebody? Yeah?
3.72.
3.72. That looks good. Acceleration, 3.7 meters per second squared. Yay, we did another force problem. Congratulations. Don't you feel very accomplished? Yes, you do. I can tell. So very accomplished for a Tuesday. Does anybody have any questions before we move to the next topic? We now have 5 forces, 5 regular common forces that we'll use repeated over and over again, and that should, well, make you smile. Why not? There, we'll give a person a tooth. Why not? I don't know. That's like the saddest thing I've ever seen. So let's move over here. All right. So what we've been doing so far is dealing with one object at a time. If you look back at that last problem, there's more than one object here, right? There's a box. There's the ground. There's the spring. There's weird spring person with the face, right? Different objects. We could have drawn a free body diagram for any one of them. We just chose to do the mass, the box, okay? At this point, we're going to start to expand a little bit and deal with multiple objects at the same time. If you have looked at the homework at all, which I'm assuming some of you have, you may have noticed that a lot of the problems deal with this. It's where we take the basic ideas that we've learned about and kind of expand them to more, I wouldn't say real life scenarios, but more like things that you might encounter, things where there's multiple objects that are interacting with each other, okay? So the best way for me to tell you how to do this is with 2 examples. So I'm going to start with just, that is not a flat line, with just a, we'll say a frictionless surface. And we're going to put 2 boxes on the surface. I'm going to call this one box B, and I'm going to call this one box A. And we're going to connect them with a string. And then over here to box A, we are going to say someone's hand is pulling on it. And since I can't draw a hand, the hand is a box labeled hand. So if I grab box A and pull, what's box B going to do? Same thing, right? If box A moves, box B has to move. They are linked together in a way. There's a connection between these two objects. They share some things, and we're going to talk about exactly what they share in just a little bit. Here is the key to dealing with multiple objects, okay? You need to focus on something. Like in the last problem, we focused on the box. We ignored that toothy grin up at the top right. We ignored all the other things that were happening and just said, as a box, what do I feel? Okay, when we did that, we were able to analyze what happens with the box, how much it accelerates, how much support it feels from the ground. Okay, we're going to do the same thing here. So what you might do is say, well, I don't really care about anything except box B. And you can just ignore the rest of the problem and find out all sorts of things about box B all by itself. Okay, we're going to do that in just a second. You might, on the other hand, say, no, I care about box A. Who cares about box B? I don't like box B. I like box A. I want to focus on it. Or you might say, well, I don't really have favorites. I care about both box and A and B equally. And maybe you decide to say, like, I'm just going to look at this whole thing all at the same time. I'm going to show you how to deal with all of those cases. The key is that you have to figure out what you're focused on. And by that, in more physics terms, we're saying be careful when defining your system. Your system is what you're focusing on, whether it's one object or a group of objects. What is your system as you get ready to draw a free body diagram and write out your equations? So let's start with two separate objects. Each one we're going to draw a free body diagram for, ignoring the other. So if I were to just draw box B, and since it's the whole thing's being pulled to the right, it's all moving this direction. We're going to call that positive X, which will make this positive Y. And then you can tell me some forces that box B is experiencing. Name one. Not this time.
I mean,
Friction?
oh, so you're ignoring A completely.
We're ignoring A completely.
Okay, so there's normal force and gravity.
Yeah, there's a normal force and gravity, so let's draw those in. So let's say this is force normal on B. Let's be specific because I don't want to confuse the two. And this will be the gravitational force on B. And what else? No friction, because we're specifically going to say this is frictionless, just to keep things kind of a little simpler so we don't have quite as much to deal with while learning something new. Your box B, what are you experiencing?
Tension.
Yeah, there's this pesky rope attached to your side, right? And something's like, I don't know what's happening over there. I don't know there's a box A, I don't know there's a hand. I only know like this rope is tugging on me, okay? So we could draw in a tension force that pulls to the right, and that's all, okay? We don't care about the hand, we don't care about box A, none of that. This is what box B experiences, okay? So from here, we can follow along a little bit and say, well, the sum of the forces in the x direction equals the mass of box B times the acceleration. And we can say that the sum of the forces in the y direction equals the mass of box B times the acceleration in the y direction. Okay? So just like before, we have a free body diagram, we have two equations. Just for now, we're ignoring all the other parts of the problem. So in the x direction, what force or forces do I have? Just the tension force, right? That's the only thing that's there. So Ft equals mb, and it certainly looks like it's moving in the x direction, so I'm going to keep that acceleration around. And let's call this equation number 1. Okay, so we found one equation. What about in the y direction? I've got one that's up and one that's down. right? So let's write those in. So I've got the normal force on box B minus the gravitational force on box B. And does it have any up or down acceleration? No, right? So this is 0, so that's 0, and now I have a second equation. Let's call that 2. Gotta say, it's kind of weird when I'm like right here. Hello. Just think about everything that's happening to make that little green line appear right in front of me. It's kind of ridiculous, isn't it? You know? Instead of just going, and I'm right here, and then it appears there. Whee! Okay, I'm done. Anyway, modern technology, the miracles that are occurring. Let's see. So that is box B. We're done with box B. That's all I can do at this point. Yes.
Why did you replace the sum of the forces with the tension force?
Because this is the sum of the forces. I only have one this time
Oh, in the x direction.
in the x direction. Yep. Good. Anybody else before we look at the second box? And this is all going to come together and wow you in just a second. So prepare yourself. I don't know if you're ready to handle the wowing that's going to occur. Box A. All right, so let's go up again and draw a separate free body diagram, this time for box A. And I'm going to again say that to the right is where it's moving, so that's my positive direction, and up is the positive y direction. And now put yourself in box A. What does it experience? Name one of the forces. Force tension to the left. Yeah, right. If you're box A, you have this rope attached to you and it's tugging that way, okay? So we could say that there is a tension force that goes here. What else? Gravitational and normal. Good. So gravitational on box A, normal on box A, and tension to the right or something to the right. Yeah, I didn't draw in like a rope pulling that way. It's just a hand. So, I don't know. Let's just call it a hand force. FH for the hand. And now that's everything that box A is feeling. Which means that we can go down here once again and say sum of the forces in the x direction equals the mass of box A times acceleration. And the sum of the forces in the y direction equals the mass of box A times the acceleration in the y direction. The right side of these will be the same as before. Yes, it's accelerating to the right. No, it's not accelerating up and down. So this is just going to be MAAX, and this one is going to be 0. And then how many forces do I have in the x direction? 2. How many forces do I have in the y direction? 2. I expected that to be faster. I was ready with my 2, but we weren't quite there yet. So the hand is pulling to the right, so that's FH. And the tension is pulling to the left, so that's negative. So there's a third equation we're going to work with. And then the y direction, one's up, one's down. It looks exactly like the other one, except it's for mass A instead. So this is force normal A minus force gravitational A. And then there's equation number 4. So if I have 2 objects, each one gets an equation, 2 equations, right? So clearly we're going to end up with 4 equations because I have to have an x and a y direction for each of them. Any complaints, questions?
Complaints are probably like, it's like twice as much work. That sounds like a reasonable complaint.
So what do you say I give you some numbers and let's actually solve for something now? Okay, so maybe, let's say, we'll let the mass of A be 10 kilograms, and the mass of B we'll say is 12 kilograms, and the force from the hand is 40 newtons. We are going to try to find the tension force and the acceleration. The tension force and the acceleration. Keep in mind, they're moving together. One moves, the other moves just like it, which means that they have to have the same acceleration, okay? But also, this is the same rope connecting both objects. That means they're gonna have the same tension as well, okay? So we could say that this is the same for both A and B. The tension force is the same for both of them, and the acceleration is the same for both of them. This links the two problems, and if you think about it, that's just connected back to what's physically there. It's physically linked by the tension, by the rope, so it makes sense that they would have the same tension as well. So, to find these these values, well, looking through here, this has tension and acceleration in it. That's two unknowns, one equation. I can't do anything with that. This doesn't have tension or acceleration, and neither does this. And this one has tension and acceleration in it. So these two equations both have my two unknowns. So let's use them. Let's say plug number 1 into number 3. So we have an equation here that's already solved for the tension force. We're going to plug it in over here for the tension force. So let's say like that. Plug number 1 into number 3. So that's going to give me FH minus MBAX equals MAAX. We're plugging equation 1 into equation 3. And I know the two masses, and I know the force from the hand, which means the only unknown there is the acceleration. So we will solve for acceleration. And then we can factor that out. Nope, I'm making mistakes. Don't let me do that. Why are you letting me make mistakes? Why? And then AX is going to be FH over MA plus MB. And somebody can plug those numbers in and tell me what you get. Anybody? How are the people outside? Are they okay? Wow, it's so much cooler right here. We should all sit on the windowsills. How good idea? What'd you get?
AX is like 1.81.
1.81. I like that. 1.81. Thank you. Meters per second squared. This is the acceleration for both of the objects to the right. How do I find the tension after that? Yeah, it doesn't really matter. I have the acceleration. I can plug it back into either of these two equations. I might as well do the easier of the two. You should get the same answer both ways. So now the tension force is MAAX. So that is 10 times 1.81. And for some reason, that is looking like a number that is different than what I have here.
Because you put 10 for mass, it should be 12 for mass.
It should be, because this is MBAX, right? Thank you. I just wrote the equation down wrong. 12. There we go. So that's 21.8 newtons. We did the problem. Don't you feel experienced with things now? You can handle this. Looking at the homework, there's a lot of stuff like this and maybe a little worse. So we're going to do another example just to make sure we're on the same page with all of it. Questions, 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 questions. Okay, if you don't have a question, let me show you one more thing. Same problem, another option. We'll call it one big object. Same problem, another option. So here I'm going to look at the case of, well, let's just say this is just one thing that's all moving together, okay? Imagine if you zoomed out, right? If we're up close, it's like, hey, look, box A, box B, and they're connected by a string. But what if I got like a long way away and just could barely see the object moving? You might not even be able to tell there's two separate objects and probably not be able to tell there's a string in between them. You'd just be like, oh, look, there's something there that's moving, okay? It's the same problem. We're just looking at it a slightly different way. So in other words, what I'm going to say this time is that my system is just the fact that I have an object that is A plus B, and there is a hand that's pulling it to the right. We're going to say that that's what we're describing now, okay? And if you think about it, it's the same, but it's different. Where'd the tension go? Where'd the string go? Where is the string? It's in here somewhere, right? Because it's kind of like A and B are both there, and the string and everything. I just combined them all together in sort of one blob. In other words, now the string, the tension force, is inside the object. It's part of the object. It's not something on the outside of the object that's like pulling on it or pushing on it. It's inside, which means that it doesn't appear in the diagram. It won't appear in the free body diagram. It won't be in the equations, which means I can't find it. So the problem asked me to specifically find the tension force as one of the things. Setting up the problem this way, I can't. There's no way for me to do it, okay? Let me try to clarify with a different example. What if you were drawing a free body diagram for me? Here I am. Draw my free body diagram. Go. Yeah, some of you right now in your mind, you just saw like arrows like pop out of me, right? It's like, boom, he's got a normal force pointing up this way. And what else? Gravity pointing straight down. That's it, right? A vector up, a vector down. That is my free body diagram, okay? Well, but at the same time, like there's more going on with me than that. I'm not that simple. I don't have just gravity and normal force. Like, I've got a liver. I don't know where it is, right? Where, biology people, I don't know. It's like in here somewhere, somebody help me. I have no idea. Liver, I don't know. Stomach, we've got a stomach in here somewhere. We've got a heart, right? Some of those things are sitting on other things, right? So like maybe my stomach is sitting on top of my liver. I don't know if it truly is or not. If that's true, then the stomach is feeling a normal force from the liver and vice versa, right? And they're all feeling gravitational forces. Like there's a lot that's going on, but that's not part of my free body diagram because those aren't forces that are outside me pushing and pulling on me. They have nothing to do with my motion. The fact that I'm just like right here, stable right now, not accelerating in any direction, is because of normal and gravity, has nothing to do with the kidney force, or the liver force, or the stomach force, or the heart force, or any other force that might be at play, okay? Those are internal forces. That's what we've done here. Now that string that's connecting the two, it's now inside. It has no impact on the motion. The only thing that's impacting the motion is the pulling, and of course, gravity and normal force, okay? See the difference between the two? Can you imagine trying to draw a free body diagram where you had to include both everything outside and everything inside? No, I don't like the sound of that at all. Then we'd have to go over here and be like, what's in the box? I need to know what's in the box. If I don't know what's in the box, I don't know how the box is going to move. Does it matter? No, all you care about is how much does the thing weigh? What's its mass, right? So let's do this anyway and see what we can find. So now we have, well, A and B. So this is A plus B. And it's moving to the right, so that's positive X. And positive Y is pointing straight up. What forces are acting on my combined system now? Name one. Yeah, all of those things that you just said. So there was a gravitational force that's down. There is a normal force that's straight up. And finally, there is this force that's coming from the hand over on the right. This is all. This is what's defining how that thing moves, the A plus B. So if I were to write out the sum of the forces in the x direction for this, keep in mind now this is mass A plus mass B, both of them are there, times the acceleration. Sum of forces in the x direction is mass A plus mass B times the acceleration, and this is the only force in the x direction. Okay, so FH equals MA plus MB times AX. So AX is going to be FH over MA plus MB. What just happened? Go back a slide. Ooh. Ah. Mm-hmm. Aha. Oh. Ah. Same exact equation, even though we approached it from a very different place. That feeling that a few of you are feeling right now, that's delight, right? There's some of you inside right now, there was just a little twinge of like, what just happened mathematically? Something about that was nice. It's the same feeling when you enter the homework question and the little green check mark goes, and you're like, I did it. I did it. This is fantastic. You're taking or receiving a little bit of delight from physics. Congratulations. It's happening. It has begun. We just started a movie right there, didn't we? It opens with, it has begun. And then who knows what comes after that. They would leave off the part about the equations, no doubt. That wouldn't be a play. So clearly we're going to get 1.82 again. Yes, we are aware things are not happening. Done? They should have a closing siren as well to let you know they're done. It should be like opposite. Like, I don't know. That's never going to happen. So you get the idea here, like tension's not involved. I can't find tension, but I can quickly find the acceleration. So what happens when you're given a problem on a test, right? And it says, find the tension. That restricts sort of which path you can go down. I have to do this. I have to have two separate objects so that the tension is actually external to my objects. If it just says, what's the acceleration? Well, you could do this, but it's going to take you 3 times as long as just going, boom, got the answer. Okay? You're starting to have like different paths to get to the same result. Does that scare you? Or does it give you just, again, the little green check mark, just a little bit inside that makes you happy? Probably some of you, it's like, yes, I did it. Others of you are like, finally! Sorry, I didn't mean to scare you. Yeah, but some of you have said that, right? Yeah? Like, I hate my computer. There's broken screens. I know, it's frustrating. Question?
Yeah. So your system in this problem is both of those things together. Right?
Yeah.
You zoomed out, so you have this one. And then the previous slide, you focused on 2 different systems, like system
Yes.
B and system A. So if you give us a problem, can we use like different systems?
You can use, yeah,
Or should we just focus on one and like stick to that?
both are equally valid. So it depends on what you're asked to find. Yeah, so you might decide on a system and go down a path and realize, uh-oh, I can't find what I'm being asked for. Let me redefine my system.
The reason I'm asking that is because in the other slide where we found acceleration so easily, like we can use this system to find acceleration and then sort of use acceleration for.
So you could start here
Yeah.
to quickly find the acceleration and then go back here and do just enough to get an equation for tension and plug that in and get tension. That'd be perfectly fine. Anyone else? Okay. Let me add a slide, which apparently I already did. When did I add this slide? I don't know. Because I want to do one more example. We're not going to work through this one in quite as much completeness, I guess. But it should help you with some of the homework problems. So let me draw something a little bit different. Let's say that we have a tabletop, and this is frictionless, and maybe the table has legs. Tables generally have legs, and usually those legs are on the floor, and maybe even one of the tables sticks through the floor a little bit. You never know. Okay? Now it looks like frictionless is the brand of the table, doesn't it? Yeah, I went to the store and I bought a frictionless table. It's very nice. It should be like, I don't know, like, there, frictionless. I feel like it should be styled or something. I don't know. Everything lowercase is kind of nice, right? I don't know, that looks like something kind of stylish. Maybe a couple of the letters are capitalized just for kicks. Maybe the F is like, ooh. Maybe we'll make the S trail down too. Clearly, I'm not in any kind of graphic design or branding, but you get the idea. Okay, frictionless. So attached to your frictionless table is a pulley, and attached to the pulley is a rope that goes this way and over this way. And we're going to say that mass A is attached here, and mass B is attached there. And once again, we're going to say it's accelerating this way, but this way happens to be down this time. So the acceleration is that way. Which means that, because they're connected by a rope, that box B is accelerating to the right. So you can kind of imagine what this system is doing. B is going to the right while A is going down, and they are linked. Okay, they're having to do the same thing. So they're going to have the same tension. They're going to have the same acceleration once again. The key is that, well, we've got this pulley in there that makes the rope turn, makes it go a different direction. So how do we handle things? Here is the key. You must have a consistent direction of motion. A consistent direction of motion. A consistent direction of motion. You must. This statement must haunt your dreams at night. Have a consistent direction of motion. You should wake up with that thought on your mind, because you're going to be doing this homework for a while, and you're going to be like, how do I solve this problem? And you'll hear, have a consistent direction of motion. And then the siren will go off, and everything will be terrible. I don't know what else is going to happen. We already did this on this problem over here. We just didn't say so. Both of them are moving to the right. The direction of motion is positive x for both of them. If I had called one of them positive y, if I decided for just whatever reason, like, I'm just going to flip my axes on the second one just to be creative. Well, then you'd have one that's accelerating in the x direction and one that's accelerating in the y direction, and then you try to plug those equations together, and then all is lost. Or even if I just decided, hey, I want my positive x to be this way, opposite on this one. Now one has a positive acceleration and one has a negative acceleration. I try to plug the equations together. There's inconsistencies. You get weird answers. Okay? The key is having a consistent direction of acceleration. So that means if I'm going to call one of these the positive x direction, I need to make that the positive x direction for the other object as well. What do I mean by that? So let's start with box B. I know it's accelerating to the right. I'm going to call that positive x, and I'm going to call up positive y. So if the acceleration is this way, and that's ax, and I know that this one is accelerating that way, I also want to call that ax. They have the same acceleration. I want to give that the same symbol, and they're going to have the same value. So in other words, I want this way to be the positive x direction. That is weird. I'm saying down. Vertically down is positive x. I'll explain in a second. And I'm not going to tell you which way y is yet. Here's what's happening. Let's say that this is my coordinate system, right? My thumb is positive x. My finger is positive y. Let your coordinate system ride the pulley. At least that's the way I think about it, right? So it's like, got that? The coordinate system is redirected by the pulley, just like the rope is redirected by the pulley. So that means my coordinate system did this. So down is now positive x. Which way is positive y? Straight to the right. That's the only way that I can be consistent with what I'm calling the direction of acceleration. Now, AX means the same thing for both of them, okay? Let the pulley redirect your coordinate system and everything will work out well, all right? So let's go ahead just to make sure that we're all on the same page and write out what forces we have. This is tension. We're going to have a gravitational force on box B and a normal force on box B, just like before. And what forces do I have on box A? There's gravity. So gravity on box A and tension. Yeah, just like that. Which means that I can write out equations. So sum of forces in the x direction for box B is MBAX, and I only have the tension force for that one. And the sum of the forces in the y direction for box B, it has no acceleration that way, so I've got the same equations I had on the previous problem. Okay. And for box A, nothing's happening in the y direction. There are no forces. So I'm not even going to write an equation for that one. Instead, we'll just have the sum of the forces in the x direction equals MAAX. This is for box A. And let's see, in the positive direction, we have FGA, and in the negative direction, we have FT equals MAAX. So that problem would set up something like that. And again, they have the same acceleration and they have the same tension. They share those two things because they're linked by a rope. Who's got questions? Anybody? We finished a little bit earlier than the other class, so I'm not going to get ahead in this class. That just messes up my brain. I don't know what's been covered where. I guess I talked faster, or you had fewer questions, or we started later in the other class. Who knows? Any questions, thoughts, comments, anything? Okay, goodbye. I'll see you in 2 days.
Yeah.